Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, so let's start. So hopefully we can go early. So all this talk about how much we can actually invest in the long run, whether the returns are mean reverting or not, whether the returns are predictable or not. Can you do the market timing? All this sort of shows you the CAPM really fails. Right? And what I sort of presented in the intertemporal CAPM or Merton's version of CAPM, we know that time horizon is important, right? So that's why we sort of want to take a second look at the CAPM model. So if you sort of take the CAPM really seriously, anything that's sort of in CAPM, that all should have this conditional information conditional on the information you already available at time t. Right, so this actually information at time t-1 for the next period returns. Right, so although I write it as this equation, you realize this first gamma should really be 0. Right, so if the CAPM is true, this coefficient, this is really just the alpha, this should be 0, right? So even if CAPM is true, the unconditional version of the CAPM, which is what we really look at when we look at the data, because we don't really know what investors are based on as the information. Well, we see the return that way. We don't really know why the return is that way based on the information the previous months. Okay? So all we can do is actually look at the returns over all the period. That's the unconditional CAPM. Right? So to get to the unconditional CAPM, we just need to take this conditional CAPM and then take the expectation on both sides. Right, so if you take the conditional on left-hand side, well, that's easy because a lot of expected returns or a lot of expected iterations. Right, you have this expectation or expect t minus 1 is just expectation itself. That's the easy part. Now, if you take the right-hand side more seriously, right, so this gamma 0 t minus 1, well, that's a constant. I can just take the mean. The expectation of gamma 1 t minus 1 times beta t minus 1, that will equal to the expectation of the gamma term, which is gamma 1, times expectation of the beta term, which is beta I. But there's still a possibility that this gamma and the beta are correlated. Right, so what we actually talked about all these market timings, talking about the sort of the investment risk, is the risk that gamma, which is the risk premium, and your beta could be actually correlated. Right? So the unconditional CAPM, which you don't have this term, is true only if the covariance of the gamma and the beta actually equal to 0. Right? So the unconditional gamma is really a very special case. And it's sort of not really very surprising the unconditional gamma fails. Right? Because if you think there's a market timing ability, if you think there's the gamma itself is not constant, at least, then this beta and the gamma are not likely to be uncorrelated. Right? So even that we sort of observe the CAPM fails because all we can do is mostly the unconditional test of the CAPM model, doesn't really mean the conditional version of the CAPM fails also. This can be also seen with defining this theta variable as the covariance of this gamma beta divided by variance of the gamma. So, this is covariance divided by variance. That's sort of the usual definition of the regression coefficient, right? So this last equation, if I divide the covariance, then times the covariance, right? So this is this is the covariance. If I divide the variance, then times the variance. So covariance divided by variance, that's my beta, and what I left is the variance. Okay? So this equation will becomes expected RIT equals to gamma 0 plus gamma 1 beta I plus the variance of the gamma times this new parameter theta I. Right? Which means the unconditional version of this conditional CAPM, you really have this new parameter that's depending on the covariance of your gamma and the beta. Right? So if you're just running the regression without the second term, you may actually end up with a positive alpha. And this positive alpha could just mean that the covariance of your gamma and the beta are possibly correlated. Right? So if you sort of see alpha, it may not be alpha at all. So sometimes people call it smart beta, because your beta actually correlates with the market return. Right, so smart beta is not really very different from alpha, just different emphasis. Okay. Now we can actually look at this problem more fundamentally from the SDF point of view, right? We haven't talked about SDF for a while, but we know that fundamentally everything can be priced by SDF, right? So remember how we derived the CAPM from SDF? We derived the CAPM saying if my SDF M equals to a linear function, A plus B times Rm, then we'll have CAPM. We derived that, right? Now let's see this process again. If I define M equal to A minus B Rm, well, you will say, why do I say minus B instead of plus B? Well, they're actually the same, right? Because it's a coefficient, a linear coefficient. If I say plus B, then my solution will be negative of this thing. Right, so the fact I use minus B, I use a plus B does not affect the solution. Okay? So if I write this SDF, A minus B Rm, then we know that this can price any of the assets, including the market return, and this can price the risk-free rate. Right, so we have two equations and the two unknowns. Two unknown is A and B. Right, two equation is for the market return and for the risk-free rate. So two equations, two unknowns, we can solve for A and B. Okay? So if we solve for A and B, what you actually observe that it's not very likely A and B actually will stay a constant. Why is that? Because if you look at this solution here, A equal to 1 over Rf plus B times expected T of Rm. So A will stay to be a constant only if the expected return is constant. Right? If this expected market return at time T, conditional return, is just a number, a constant, then A is a constant. Right? And then B is possibly a constant as well. But as long as your expected return of the market conditionally is a changing variable, then your A and the B is not a constant. In fact, we should call it AT and BT. Right? So fundamentally, this shows you that as long as the expected market return is fluctuating, then CAPM should not be actually unconditional. CAPM should always be a conditional CAPM. And I already show you lots of evidence that expected market return is actually not constant. It's a changing variable. Right? Then what can we do with it? Right? Well, we have this nice theory that's CAPM, but suddenly you are telling me CAPM is not true, it's only true conditionally. Right? How can we do it? Well, one way is we just do it conditionally. Right? But the problem with that is I don't really know what you are conditioning on. I'm just a researcher. I'm not really doing the investment myself. Even if I'm doing the investment myself, I don't know what the other information set is. Right? So we have to sort of find an unconditional version that's testable with the conditional CAPM. One solution is to use what's called instrument. Let's say there is some variable z, zt, that can predict this AT and BT in the SDF. Right? So what could those zt be? What kind of thing is probably be able to sort of predict the SDF coefficients. Well, somebody will say DP ratio. That's a fair answer, right? Because DP ratio can predict the expected return conditionally, market return, right? But it's also size factor, the value factor, right? So all these so-called firm characteristics, once we form a portfolio, these characteristics can sort of predict the future market expected return. Right? Anything that can predict future market return, that's observable at this day t. Right, so we can use it as the instrument that's predicting A and B. But the interesting thing that once you think there's an instrument that can predict A and B, now our SDF linear function, if we just plug in this ft plus 1 with A and B, right? So this will be A plus A1 zt plus B0 plus B1 zt times ft plus 1. And then if I collect the terms, my one-factor model, conditionally, now becomes 1, 2, 3, a three-factor model. Right? So we start with this linear expression for the SDF, right? And this is all conditional on time t plus 1. And because we know what AT is just A0 plus A1 times Z, so A0 plus A1 times Z. Now we know what BT is. BT is just B0 plus B1 times Z, right? So B0 plus B1 times Z, that times F. Now I can collect the terms. So instead of one-factor model, now I have 1, 2, 3 factors. I have firm characteristic self, I have market return, and some combination of the two. A linear transformation of the firm characteristic, ZT variable, and FT plus 1 variable. Right, so this actually gives the support of the multi-factor model. Right, even if you think really there should be only one factor, that's market return. But because this one-factor model is not observable period by period, when we take the unconditional expectation, this one-factor model, conditional on some instrument ZT, becomes a multi-factor model. Okay? So does that mean, all the Kaplan tests we have been doing is actually not valid? The answer is no. Why is that? Just use this idea of instrument, right? When we do the pricing, fundamental pricing formula equals to P equal to expected M times X. Remember that? Right? So the problem is, M and X is actually correlated. M is not observable. And M is, as we just seen, is correlated with market return itself, the coefficient A and B. Right? Now just use this instrument idea. Instead of just looking at the price of each individual asset, if I can find the ZT as an instrument, now I look at PT times ZT. The unconditional version of the PT times ZT is actually true. But what is PT times ZT? Or what is XT times ZT? Well, if you think about this ZT as instrument that's sort of the weight that's dependent on the firm characteristics, then this ZT, PT times ZT is just portfolio return. And the payoff is just portfolio payoff, right? So if, as we said, ZT is something that's dependent on the firm characteristics, then all the tests that we do, depending on the size portfolio, depending on the value portfolio, depending on a lot of characteristics, is just doing the Kaplan test with the instrument variable. We're not really doing it, just forming the portfolio randomly. Right? We are doing it with the formed portfolio depending on some characteristics. And this depending on characteristics really fundamentally is just the instrument using the managed portfolio. Right, so the approach we actually did is actually still can be seen as instrument. It's not just instantly invalid. But sometimes people take a different approach, right? So one approach is, what if we can estimate the beta? That'd be great, right? If we can estimate the beta at each t, then we can use the conditional model. But what's the challenge of that? If you have, for example, monthly data, can you estimate a conditional model in monthly frequency? If I give you monthly data, right, I'll say, give me a test of conditional beta using the monthly return frequency. Can you do that? Yes. In the conditional model, you will need beta t, right? And this t, the data I give you should be monthly. Can you estimate monthly beta with monthly returns? Yes? Please do the research with me. I can't figure out the way. It's not possible. If I have monthly returns, I only observe the returns monthly. But in order to estimate beta, I need many returns. So I cannot estimate monthly beta with monthly return. You see what I mean? Because estimate the beta, you need time series, right? So in order to actually estimate beta, you either have to go a higher frequency of returns, like daily data, or your testing period must be semi-annual or annual. Well, even if you do testing period annually, you only have 12 data points to estimate beta. The error is huge. Right? So I think what this paper does is actually using the daily data, but the estimate period will be quarterly, semi-annually, and annually. So they'll have more sort of stable estimate of beta, right? So in any way, so they estimated beta dynamically, right? And then trying to test this Kaplan model conditionally. When the beta changes, what is this changing beta the only determinant of the changing expected return of the stock? That's the question, right? And what this table reports is the alpha estimates using this conditional beta, using this changing beta with the conditional model. Right, so with the conditional model, they calculate, most of these alphas are fine, right? As we already said, this small, really small, and the growth stock always have problems, right? But most of the problem, again, is in the value portfolio. The value premium is still there, right? And the value minus growth, which is V minus G here, is positively significant. Because this bolded font meaning it's significant. All right, so what they find is even if you go to the conditional model, this value premium still doesn't go away. The momentum premium still doesn't go away. But lots of this size premium looks fine, except the very small one in the quarterly data. Right, so momentum winner minus loser still positive. Value high book to market minus low book to market is still positive. Right, so even we think the conditional model is true, but empirical it's sort of struggle to sort of approve this is true. There's actually a more sort of succinct approach. This is from the same paper, Lawanlo and Nagao. Nagao used to be at University of Michigan, where the graduate, now he moved to University of Chicago. So they have this paper in 2006. What they actually found is a very sort of succinct argument. They find out, as we can find out, the value portfolio, HML, have this unconditional monthly alpha of about 0.59%, monthly alpha, right? The monthly risk premium, the market risk premium, have this standard deviation of 0.5%. That's also very easy to estimate, right? This standard deviation of the HML beta, remember they were doing the dynamic beta, right? Estimate beta period by period, then they can estimate the standard deviation of that beta. The standard deviation of that beta is 0.3%. They argue that these three numbers means the conditional CAPM cannot explain the observed HML premium. Why is that? By the way, this used to be a question on the exam. Because it's really easy to do, but you need to think. There's not a lot of calculation, right? You have only like 3 numbers. So why the covariance which with which? What are we looking at? What should be the sort of alpha in terms of the unconditional model? What should the alpha be? Just go back slides, a couple more slides. Here. The answer is right on this slide, right? What's the maximum possible value for alpha in terms of the conditional model if we look at the estimates unconditionally? You have this equation, well, this doesn't really matter. The unconditional is just this equation, right? As I just talked about, what's the alpha? What can be mistaken as alpha? This term, right? So if this term, the covariance of gamma and the beta is positive, even if this is 0, as it should be, you still observe alpha unconditionally, right? Everyone get this? This is, I don't know, it's the sort of the really dreaded, the feared silence. I'm really afraid of such a silence, right? Because remember, this is the conditional model, right? What I did is take this conditional model to the unconditional model. So I have this extra term here, right? But if I just run the regression, expected return equals to some intercept plus something times the market premium, I'll get this coefficient alpha, the intercept, just at this term. Even my gamma 0 is 0. Right? So this covariance is what's determining how much we can observe unconditionally, given that conditional model is true. Okay? So unconditional alpha, given the conditional model is true, is covariance of this gamma and the beta. Now let's see. What's the covariance? Covariance is rho times standard deviation x standard deviation y. Right? So rho times the standard deviation of beta times the standard deviation of gamma. And we know rho maximum value is 1. So it must be less than standard deviation of beta, which is 0.3. And standard deviation of gamma, which is 0.5%. So this is, the answer is less than 0.15%, but what we observe, the alpha of the HML is 0.59%. So that shows the unconditional, so the conditional model still cannot explain the alpha we observe. Okay, so I got lots of students asking me, what kind of question you ask? Can you give me examples? I already give you lots of examples, right? As you can see, they are not difficult, right? They don't involve a lot of calculations. They don't ask you to memorize a lot of things, but you just need to understand. That's the whole point, right? Yeah. So, good luck. I'll give you assignment tomorrow. That's it for today.这个是要 JavaScript。对 ，update 过。 觉得应该是 update 过。你这个也是今天的吗？还是没有？对啊，你去看那个 update 过的，应该是有 update。对啊，如果你说这个是 zero 的话，对吧？对啊，如果说这个是 zero， 这个是 zero， 这个是 zero 就是开盘，这个是 zero， 对不对？然后你问我觉得你应该 OK 吧？这个是大于这个就是阿尔法。它是可以再去下约也可以，因为阿尔法没有过多少有用的。OK， 那这个就是阿尔法。那这个阿尔法如果从 conditional model 来讲，就是 covariance。OK， 那因为这个 covariance， 我们能够算出来的最大就是0.15，0.15，对吧？那么说明这个 gamma zero 就不是0.59。
智商不够，发现
这个智商，这跟智商没太大关系吧？
有啊。
啊？
教的这些东西，在题目提到的时候，
期末会给我们一些练习题吗？
啊？
会给我们一些练习题吗？狂做让我们。
有的也不会很多的，我这个不是用这个题海战术做出来的，因为这个东西没有办法题海战术。
理解了。
你如果全都被做完了，这个就跟 GRE 题一样的。
好。拜拜。
好，拜拜。
你现在教我们这些东西，就是在美国和国内是不是并不是最后一学期才学，很早就会学的吗？的确是非常简单。
看是什么课，什么 level 的课。
你现在教的内容的确是 advanced 的。然后每次看你在上课就在叹气，我就觉得是不是我其实都是大一、大二就学过的。
那没有，大一、大二不应该学过，但是呢，如果你们大一、大二有学过的话，就是那些 equation 就比较容易讲。就说内容是 advanced， 但这个方法其实很多也没有那么 advanced。
我觉得有点跳跃，有点厉害。从一个本科生的角度，
我觉得对本科生来说可能是比较难，就是你的这个数学的和统计的准备知识的问题。
特别是如果说我们本科学的是 capital market 的话，我们 AU 本科反正是有2个 major， 一个是 capital market， 一个是 quantitative finance。如果是 capital market 的话，它是几乎是没有任何数学方面的课，只有2个统计是讲 regression。所以一下就来搞这个，我就
就如果是以